Okay, but it's only one case. Okay, it's only one case. I'm going to ask you guys to prove the other two, but I'll start by drawing the diagrams for you. Okay? If a is equal to 90, right? This is the easy one. Remember I said here, the center of the circle is inside the triangle. Okay? If my corner angle that I'm interested in is 90 degrees, for instance, let's actually draw, that's 90 degrees. Let's make that A. Okay? And now I need the other side of the triangle, like so. Where does the center lie in relation to this triangle? Answer?
It's on the middle of it.
Fantastic. It's on, well that's O, right? It's on this A length, little a, that I'm looking for. It's the hypotenuse of this triangle, right? So I have A all the way across here, right? But, because the angle of the semicircle, it's also the diameter. There's the setup, okay? That's for case 2. For case 3, the center will not be inside the triangle, and the center will not be on the triangle. Where do you think I'm going to be with an obtuse angle?
Outside.
The center, put it there, okay, is going to be outside, because look what happens if A is obtuse, like that. Like that's an obtuse angle. Call that A, right? Look at what's going to happen to little a, right? It's not going to be close enough to the center. Okay, so there's A, little a. Right? So I proved it for you for case 1, that this is equal to the diameter of the circumcircle. Give it a go for case 2 and case 3. You'll need slightly different ways to do it. That's why we have different cases. But give it a try. And if you think you have an idea, call me over and I'll have a look. First, let me deal with a way not to prove it for case 2.
Oh yeah.
Okay? So let me get another color, okay? Now, so here's what I've had suggested to me, okay? And admittedly, it's not that far from the truth, but I'll show you why this method doesn't work, okay? So here's what I've had suggested to me. Look, it's a right angle triangle, right? Right angle triangle. So if I want sine A, right? Well, sine is opposite on hypotenuse, isn't it?
Yeah.
Isn't it? Now A's over here, so the opposite side, you can write it as A or as D because they're the same, right? So you could, for example, you could write it, A would be what you wanted, right? That's the opposite side. And then you can say it's opposite on hypotenuse, and the hypotenuse, I can write it as D, right? And then you swap them around and you're like, yeah, I'm so cool. No, you're not. Okay, now let me show you why. Let me show you why. Because it does seem kind of instinctive, right? I'll tell you why not. This highlights one of the reasons why we had to move away from triangles, specifically right angle triangles, and to the unit circle in order to define what sine and cosine mean. Sine and cosine have no meaning when applied to 90 degrees in a right angled triangle. It doesn't work. Now it almost looks like it works for sine, but you can see as soon as I go to cosine, you can see how it breaks down, okay? Because cosine is adjacent on hypotenuse, apparently, right? But if I'm here, which adjacent side do I want? Because I got 2 of them, right? And it turns out that not only is it like hard to choose which one, it's hard to choose because you can't choose either of them. Because cos of 90 degrees is in fact 0, right? Which doesn't make sense in a triangle, okay? So sine and cosine you can't really apply to the right angle in a right angle triangle. It only works with the other 2, okay? So therefore, what can we do with this? Well, the proof I'm going to show you almost looks as much of a trick as this, but, and Aaron got it, it is actually mathematically sound. Okay? Just don't move, it'll go.
Oh my god.
This is math.
Is anyone allergic?
Oh my god.
No, is anyone actually allergic?
It's on the page. Oh. Stay still.
And Ron's gonna have a panic attack.
Where's it going?
Oh no. Stay still.
It's at the front now.
It's right here.
Man, you guys think this is bad, I remember once a bird flew into my class.
Bird flew into what?
It's gone. Should we shut the windows? Shut the windows.
Bird came in, I would cry.
Yeah, a bird flew into my class once, and it was like, and it was not a very clever bird, and it was like, it was trying to get out through all the shut windows, and it's like, ah, what have you done to me? Okay, yep.
A dragonfly came in.
Dragonflies are harmless and awesome.
Jack, he went over and grabbed his boy and just carried on like, it was just lazy.
That's awesome.
He came back again 2 minutes later.
It's like, hey, you're cool. Hey, okay, Rich. So now that all dangerous threats have left the classroom, can we refocus? Can we
I think I got it.
Alright, well let me show you. So here's what I'm going to say. Forget about this triangle for a second. Something that you know is true before you arrive at this is this. We've known this for a while now, right? We defined it on the unit circle, and that's what we got, okay? But this means that sine of 90 equals 1, right? Sine of any angle that's also equal to 90 will also be 1. You agree with that? Right? Any angle that's equal to 90, you can pop in there. And I have one. It's A. Right? So I can say sine A equals 1. You agree with that? Yeah. Okay. So one of the handy things about 1 is that 1 is its own reciprocal. Right? 1 is its own reciprocal. So I'm going to take the reciprocal of the left and the reciprocal of the right. And that will give me this. You happy with that so far? Okay, watch. I'm going to multiply both sides by A. Because A is just a number. It's just a length, right? There's no problem with that. So I'm going to multiply this side by A and this side by A. Right?
Oh, that's so lucky.
But A happens to also be equal to D.
Oh, that's
So I'm done. Okay.